Is.
Hold up, let me say.
Yeah. Right. Four.
I forgot my president is in this
Yeah,
class.
we really could. A single letter can so much change the meaning of that, you know? And it's honestly challenged.
I have two residents in this class.
Yeah?
I forgot, yeah.
Yeah.
Like not really for our conversation.
All right. So now we know what the weight function does for small values of L. I'm sorry, for small values of R. This argument doesn't work if L is equal to 0 because this term goes away. So the argument doesn't work, but the result does. It turns out that it goes like R if L is equal to 1, but not for this reason. But it still goes like R to the 0 plus 1. It goes like R if L is equal to 0. So right result, wrong reasons in that case. But anyway, now let's look at the other limit. As R goes to infinity, then, well, assuming that V is going to 0 and what's this thing doing as R goes to infinity?
0.
Going to 0, right. So if R is going to 0, then if V is going to 0 too, we can say that d squared u sub e dr squared is approximately equal to minus 2me over h bar squared. Now I just say u, not even an L subscript. Here I've dropped the L subscript because, well, now I'm saying that the first two terms go to 0, so as long as E isn't 0, E is dominating for large values of R in that expression. And actually minus E is dominating, so when I take that over to the other side, it's a plus E, so now I've got a minus sign still there. So this turns into d squared ue dr squared is equal to minus 2me over r squared ue because E in magnitude is going to be much, much greater than L plus 1 over 2m r squared as R goes to infinity. So L's not going to matter anymore. Only E is going to matter. So I only have an E subscript on my U. I mean, it's still UEL, but the point is you get the same thing for all values of L in this thing. Yes?
So you mix the h bar
Where? Let's see.
L.
Yeah, true.
What?
Yeah.
Yeah, E is much bigger than the L terms, but how about the VR?
Oh, I said, and let's suppose V goes to 0 too. Let's, like the Coulomb potential, for example, goes to 0 as R goes to infinity. Right. So I'm assuming both these guys go away, so that only E is left.
So we're working in the Coulomb.
No, I'm working with any V that goes away as R goes to infinity. The Coulomb potential is an example of that. But we're letting, just in general, I just want V to go away. I want the effective potential really to go away as R goes to infinity there. So hence, if V goes to 0, as R goes to infinity, then if V goes to 0, we have this. Two cases. E is greater than 0. If E is greater than 0, can the particle get out to infinity, classically speaking? Right, go back to our kind of generic plot of a typical effective potential. If E is up here, can the particle escape to infinity? Yeah, because it would have positive kinetic energy at every value. value of R, because the effective potential is going to 0 there. So for E greater than 0, particle can escape to infinity. Whee, I'm free! Escape to infinity classically. And then U sub E is going to oscillate in that case, because E is greater than 0, so second derivative of UE is some minus thing times UE itself. And so therefore, you just can't help yourself, can you? And so therefore, oscillation occurs. So now I have a vision of her standing up and going like this as she walks across the room. I think you should do that. Okay.
I think we should go on.
All right. UE oscillates as R goes to infinity. So UE is going to look something like AE to the IKR plus BE to the minus IKR, where K squared is 2ME over H bar squared, the usual sort of definition we make. If E is less than 0, classically, can the particle get out to infinity? Nope, because out here it would have negative kinetic energy, so a classical particle would go, yeah, stop and bounce back. A classical particle would bounce back and forth between these two limits, so to speak. That shows up for gravity in classical physics. It shows up as an elliptical orbit. There's a minimum R value and a maximum R value. The planet gets some closest point to the sun, some furthest point from the sun. Here in quantum mechanics, it shows up as the wave function is exponential as you go out to infinity. Particle cannot escape to infinity classically. It's in jail. And so UE is going to look like AE to the AE to the, I'm going to make it minus kappa R plus BE to the plus kappa R, where kappa by definition is square root of minus 2ME over H bar squared, which is real because E is negative, and so minus 2ME is positive, so that's a real number. This is the origin of energy quantization when E is less than 0. In both cases, B divided by A is determined by the requirement that U approaches R to the L plus 1, which goes to 0, as R goes to 0, when the solution is continued to the origin. If E is greater than 0, you get a solution for every value of E, and the ratio of A to B is set by the fact that the solution has to approach 0 as you go to the origin. But there's an additional condition. For E less than 0, we must origin looks like A e to the minus kappa r plus B e to the kappa r. And I want a function I can normalize. B has to do what? Has to be 0. Yeah, because otherwise the wave function would blow up as r goes to infinity and it won't be normalizable. For energies greater than 0, these things just wiggle, so we don't worry so much about that normalization business, just like in one dimension before. We can look at those as scattering solutions. But if we want downstate solutions, we need a normalizable wave function, not one that rose up good. We need V equals 0 so that psi will be normalizable. Only for specific E, there's multiple ones, only for specific E's does this occur. In other words, energy quantization. So again, I emphasize, it's not the Schrodinger equation per se that leads to the quantization of energies in quantum mechanics. It's always the boundary conditions. It's the boundary conditions that put the quantum into quantum mechanics, not the Schrodinger equation. Question?
We're not going to consider the scattering case?
We're not going to consider the scattering case, no.
Oh.
Yeah, that would be a hypothetical quantum 2 that would consider the scattering case. Then it becomes quite interesting. Not now. That's another beast entirely. Yeah, you have to do partial wave analysis, and it gets pretty messy because, one dimension is bad enough, but in 3 dimensions you have to worry about the waves spreading away from the origin, and you have to write the incoming plane wave as a superposition of spherical harmonics, and it gets entertaining, shall we say. So we're not going to be entertained, sadly, with that. I need to be careful because you might see the tear that's starting to well up in my eye as I think about that, but I don't know, maybe another time. Okay, so hydrogen. For reals now. We're really going to do it this time. Now we're actually going to take the Coulomb potential and really work with it. Before, up to this point, we've been saying general things about the form of the U's, but now let's be specific. Radial equation for H is obtained. What did I do? Oh, okay. All right. Radial equation for H is obtained by substituting F. V of R is equal to minus E squared over 4 pi epsilon naught R to obtain D squared dr squared plus 2m over h bar squared E plus E squared over 4 pi epsilon naught R minus L plus 1 h bar squared over 2m r squared. All that times UEL is equal to 0. So I multiply multiplied through by a minus 1, because remember before the d squared, the r squared term had a minus sign in front of it, and the e had a minus sign in front of it when I had it over on the left-hand side. I've multiplied through by a minus 1, that's why this is plus e squared over 4 pi epsilon r, and why this is minus ll plus 1 h bar squared over 2mr squared. So, this is our task. We want to solve this differential equation. Now, how many of you have solved differential equations by doing a power series substitution before? You've seen that sort of thing before? Yeah, okay, so we're going to do that. We're going to substitute a power series. We could try a power series of the form UEL is equal to sum from n equals 0 to infinity of c sub n r to the nth power, but that turns out not to be quite what we want to do. It would work, but it would be more painful than what we're going to do. But we're going to use what we already know. Since UEL as r goes to infinity goes to e to the minus kappa r. That's what we just said before, that for large r, the solution approaches asymptotically an exponential function, which needs to be a decaying exponential so that the wave function doesn't blow up. Actually, I should say some constant times e to the minus kappa r. Where kappa is equal to the square root of minus 2me over h bar squared, which we're going to call the square root of 2mw over h bar squared, where w is minus e is the binding energy So in other words, what is the energy of the ground state of hydrogen? It's minus 13.6 electron volts. That means the binding energy is 13.6 electron volts. The binding energy is how much energy it would take to strip the electron off, to just barely ionize it, to remove the electron. So the binding energy is minus the energy. It's the energy you need to put in to get the energy back up to 0, to get it back to a situation where the electron and proton have been separated from one another. So we're doing that just because it's fun to have something positive instead of negative to keep talking about. So W for hydrogen, we will discover in the ground state is plus 13.6 electron volts, and in general it's 13.6 electron volts over n squared. Anyway, we're going to switch to a new variable rho, and rho is going to be equal to 2mw over h bar squared, the square root of all that. So all that to the 1/2 power times r, which is a constant. For a given energy, w is some constant. So we're just defining a new variable, which is a constant, that thing we call kappa before, times r. So rho is kappa r. Kappa is root 2mw over h bar squared. So that 1 over r is equal to 2mw over h bar squared to the 1/2 times 1 over rho. So if I just take reciprocals basically and then move the 2mw back to the other side, is this, then 1 over r is that times 1 over rho. So we're going to change the variable, it'll turn out that's convenient. gets rid of some nasty factors that would otherwise be hanging out to torture us. And we're going to define UEL is equal to e to the minus rho times VEL. That's a little v, not a big V, because big V is the potential. So that's a cute little v right there. So in other words, this is the definition of VEL in terms of UEL. So what are we doing this for? Because it turns out the equation we get for VEL will be simpler than what we would have gotten for UEL in the end.
So this V has nothing to do with potential.
No, that's correct. That's correct. It's nothing to do with it's a small v. It's just a new function, little v sub EL is a function part.
Why it's called V and not V?
No, there's no reason other than people get tired of coming up with new symbols. So VEL will tell us the details of how UEL differs from its asymptotic form. So in other words, we know that UEL looks like e to the minus rho for large R. So for large R, we know that VEL is going to go to some constant because we know that UEL looks like e to the minus rho for large R. So VEL must go to some constant in large R. And then, in general, the form of VEL will tell us the details of how UEL isn't exactly e to the minus rho. It just becomes that for large R, but for small r, the VEL will tell us the details of the difference between U and its asymptotic form. And if you're not entirely clear about that, well, just keep watching and things are going to drop out for us here. So, question? Okay.
That line doesn't.
What? Just,
So you're saying that as R goes to infinity?
as R goes to infinity, we know that UEL looks like e to the minus rho.
Yeah.
So we're saying that UEL is what it does at large R times something that gives us the details of what it does at other values of R, so to speak. Yeah, so VEL kind of tells us how the details of how UEL differs from what it does at large values of R. Okay, now, once again, we need to do our change of variables. So, and again, so why are we doing this? Because the resulting equations are simpler than if we didn't do this, so it is worth it. Because DDR is equal to d rho dr times dd rho. That's just the chain rule. The DDR operator is dd rho operator times d rho dr, which is 2mw over h bar squared to the 1/2 times d rho, just because of the fact that d rho dr is that. Now, given that rho is square root of junk times r, then d rho dr is square root of junk. So ddr is square root of junk times dd rho, since d rho dr is that, is this. And then d squared dr squared, then you just do it again, d squared dr squared will be 2 powers of junk times d squared d rho squared. So it's just 2mw over h bar squared d squared d rho squared. Then, if we want to rewrite this expression in terms of rho and in terms of v, our early expression becomes 2mw over h bar squared, there's an open curly brace here, 2mw over h bar squared, d squared d rho squared, minus 2mw over h bar squared, plus 2m over h bar squared, 2mw over h bar squared to the 1/2, e squared over 4 pi epsilon naught rho, minus, good lord, h bar squared over 2mw 2m over h bar squared L plus 1 h bar squared over 2m rho squared, all that times e to the minus rho VEL is equal to 0. So I've substituted e to the minus rho VEL for UEL over there, and then I've substituted for the derivatives and for the r's in terms of the rhos. And then we get some canceling. That 2m cancels that 2m. That h bar squared cancels that h bar squared. Okay, any questions? Pencils catch up to all that. Melting point, solubility, ionic solid, covalent. Looks like chemistry. Multiply through by h bar squared over 2mw, because notice that there's h bar squareds over 2mw's lurking in terms over there. And this whole thing then finally turns into d squared d rho squared minus 1 plus 2m over h bar squared w, the quantity to the 1/2, e squared over 4 pi epsilon naught rho, minus L plus 1 over rho squared, e to the minus rho, VEL is equal to 0. So now this is the equation that we want to solve. Could it get any better? Why, yes, it could. Now we're having d squared d rho squared of e to the minus rho VEL. Let's simplify that, shall we? So that's going to be d rho of e to the minus rho VEL. So what's d rho of e to the minus rho VEL? Just minus 1 e to the minus, because derivative with respect to rho of e to the minus rho is minus e to the minus rho, right? So this will be minus e to the minus rho VEL plus, and then we'll have the e to the minus rho times the derivative minus rho VEL. Okay, so time to go nuts again and then discover, oh, things cancel out partly. So that will be, if I take dd rho of all that garbage, I get 4 terms. I get e to the minus rho VEL minus e to the minus rho dVEL d rho minus e to the minus rho dVEL d rho plus e to the minus rho d squared VEL d rho squared. Actually, I don't get canceling out, I get terms grouping. So, better slow down, these people are still copying. So notice those middle two terms become minus 2 e to the minus rho dVEL rho. There's a factor of e to the minus rho in every one of those terms. So d squared d rho squared e to the minus rho VEL, there's a factor of e to the minus rho in every term, so I'm going to pull that out to the front. E to the minus rho times d squared VEL d rho squared from the last piece over there, minus 2 dVEL d rho from the middle two pieces, and then plus, so notice here we have a minus 1 e to the minus rho VEL, and that second derivative with respect to rho squared pulled in an e to the minus rho VEL. So those terms cancel each other. And we get plus e squared lambda over rho minus L plus 1 over rho squared VEL is equal to 0, where lambda, by definition, is 1 over 4 pi epsilon naught times 2m over h bar squared w to the 1/2 power. So there's all that crap multiplying e squared, so I just take all that together and define it to be lambda without the rho, and define all that to be lambda, just because we get tiresome and keep writing it. So the first two terms here come from all of that, from our second derivative of e to the minus rho VEL. The first term cancels with this minus e to the minus rho VEL. And then the last two terms are just these two terms where I've taken all this stuff that I drew a box around and redefined it to be lambda. This is what we're going to do a power series solution on. The e to the minus rho cancels because it's factored out and the whole thing's equal to 0. So I can just cross off that e to the minus rho. So my final equation that I'm trying to solve now is this thing, that the stuff here in the square brackets is equal to 0. That's the equation that I'm going to solve. So far it's been a simple 402-step procedure. Now we're again going to use something we already know. We already know that UEL looks like rho to the L plus 1 as rho goes to 0. So we're going to write that VEL is rho to the L plus 1 times a power series k equals 0 to infinity of C sub k rho sub k, rho to the k power. Because then for very small rho, for very small r in other words, the first term dominates. The first term in that series is C sub k 0 to the k, for rho goes to 0. So in other words, C sub 0 becomes the only term that survives as rho goes to 0. And so then you get that VEL was going like rho to the L plus 1. So in other words, we make our series be summed from k equals 0 of C sub k times rho to the power of k plus L plus 1. We're going to make that substitution, that VEL is the sum of C sub k rho to the k plus L plus 1, k equals 0 to infinity. And then that will have automatically the right asymptotic behavior as rho goes to 0. Because the very first term in it will be rho to the L plus 1 times C sub 0. Any questions? Doubtful. People are looking like, what are we doing? But it's all going to work out. It's also going to be something where you got to look at it again, in order to get this to soak in. You really do. I know I certainly have to look at it. Every time I do this, I have to look at it again, basically. All right. So we are going to substitute that in for VEL. We're going to substitute our power series in for VEL, and then find a recursion relation between the coefficients in that expansion. So if I substitute in VEL is the sum of the CK rho to the k plus L plus 1, what's the first derivative? It's the sum from k equals 0 to infinity of what? CK times what? Yeah, what's the derivative of rho to the k plus L plus 1? Exactly. It's equal to, for each term, each term you've got CK, rho to the k plus L plus 1. If I take the derivative of each term with respect to rho, well, you just do the ordinary rules for taking a derivative. So you're going to get CK times k plus L plus 1 times rho to the k plus L plus 1 minus 1. Or in other words, just rho to the k plus L. And then what's the second derivative? What's d squared VEL d rho squared? Well, that'll be sum from k equals 0 to infinity, c sub k times what? You got it. That's right. It's going to be equal to k plus ck, k plus L plus 1, and then when we take this derivative, we're going to get k plus L down there. And then I'm going to pull one more power down from rho, so it'll be k plus plus L minus 1 is the power of rho. So now we substitute those expansions back into our Diffie cube. I substitute our expression for d squared vd rho squared, for dvd rho, and for v itself. That's the deal with a power series solution, is you take the power series and its derivatives, plug them back into the original equation, and then you say, the whole thing has to be equal to 0, and the only way it'll work for all values of rho is if the coefficient of each power of rho is equal to 0. Yeah, no, I'll do it and then I'll say it again. So let's plug these guys back into our differential equation. So this says that the sum from k equals 0 to infinity of c sub k, k plus L plus 1, k plus L, rho to the k plus L minus 1. So that's the first term, that's d squared vd rho squared. The second term, I'm going to get minus 2 dvd rho, so I'll get minus the sum of 2 c sub k, k plus L plus 1, rho to the k plus L, so I've substituted in dvd rho, times minus 2. So I just took my power series expansion for dvd rho and substituted it in that second piece there, minus 2 dvd rho. Plus, and then we're going to get e squared lambda over rho times VEL. So that'll give me plus e squared lambda, and then for VEL, my original VEL, I have to here divide by rho. So that pulls down 1 power there. So I get plus e squared lambda times the sum from k equals 0 to infinity of c sub k rho to the k plus L, not k plus L plus 1, because I'm dividing through by rho here. So that divides each rho plus k plus L plus 1. Each one gets divided by rho, so it just turns into rho to the k plus L. And then, on the last term, I'm dividing through by rho squared, so every term has the power of rho diminished by 2. So the last term becomes minus L plus 1, sum from k equals 0 to infinity of c sub k rho to the k plus L minus 1, because I've divided rho to the k plus L plus 1 by rho squared, so I subtract 2 from the exponent to make it rho to the k plus L minus 1. All that has to be equal to 0. And this is standard stuff. This is the standard technique for solving a differential equation by using a power series. So here's where I repeat what I told you I wouldn't repeat until I actually did it again. For the left-hand side to equal 0 for all rho, because that's what we want. We want that to be 0 for all rho. The coefficients of every power of rho have to vanish. Because the only way to make a polynomial be 0 everywhere is for every coefficient of the polynomial to be 0. This is a polynomial in rho. If it's to be 0 everywhere, every coefficient has to be identically equal to 0. That's going to give us a relation between the c sub k's that tells us how to write the expression for our solution. But there's one thing that is convenient to do before that, and that is, notice that the different terms have different powers of rho in them. These two terms have rho to the k plus L minus 1. These two terms have rho to the k plus L. So, to facilitate the analysis, we're going to rewrite as, and that'll be the last thing we do today, this first term, we're going to change it. The sum from k equals minus 1 to infinity instead of 0 to infinity of c sub k plus 1. We're doing summation by substitution, so to speak, instead of integration by substitution. C sub k plus 1 times k plus L plus 2 times k plus L plus 1 times rho to the k plus L plus 1. Why can I do that? Look carefully at what happens here. The first term in this summation, if I put in k equals 0, the first term is C0 L plus 1 times L times rho to the L minus 1. Right? If I put in k equals 0, the first term is C0 L plus 1 times L times rho to the L minus 1. Now go down here. The first term has k equals minus 1. What is that term equal to? Well, this is c sub k plus 1. So if I put in k equals minus 1, I get c sub 0. Here, if I put in k equals minus 1, k plus L plus 2 simplifies to L plus 1. Just like over here for k equals 0. The second piece, k plus L plus 1, if I put in k equals minus 1, becomes just L, just like it was over here. And then for k equals minus 1, rho to the k plus L plus 1 becomes rho to the L. That's actually, I think I have a mistake. K plus L minus 1 is what I want right there. K plus L minus 1. No, k plus L. K plus L. I just want k plus L there. That's what I just want k plus L there. Because the whole point is I want all the terms to have rho to the k plus L as their power there. So this last piece, if I put in k equals minus 1, becomes rho to the L minus 1. That's exactly what this one does for k equals 0. So the point of all that is the first term is exactly the same when I do this, and so is every other term. In other words, the second term in this series is the same as the second term in this series. So convince yourself of that. And then we'll finish by writing out the rest of it. The other pieces stay exactly like they were before. Now, in your notes, you should probably actually put them in. And then the last piece becomes minus the sum from k equals minus 1 to infinity of L plus 1, c sub k plus 1, rho to the k plus L is equal to 0. And then the point of all this is now every term is a series where the powers are rho to the k plus L, and then that means that if I collect the coefficients, every set of coefficients has to be 0 when you collect them together. And next time, we'll see what the implications of that are. We'll see that we get a recursion relation which tells you what is ck plus 1 in terms of c sub k in order to make the coefficient of rho to the k plus L be 0. And then we will discover that the resulting solution will blow up unless the series terminates somewhere. And where the series terminates actually is determined, it actually is what defines the principal quantum number. And so that's where that n comes from, we will see. It's because the series has to terminate or it will blow up. And that will lead to the idea that L has to be going from 0 to n minus 1 and all that sort of thing. So that's where it's going to come from. All right, the end for today. So next time, it'll be glorious. We're going to get hydrogen. And then we're going to get dizzy because we're going to start spinning, so to speak. We'll show how to put spin in the wave functions.